Hello, if you're watching this video, I'm hoping that you have completed all of the questions on the study guide that I sent out the other day. And so you're just going to kind of review and check your answers compared to what I have here. If you haven't done that, you will need out paper, pencil, periodic table, scientific calculator, all the things that you're going to need for your test. All right, so again, it starts out with the characteristics of acids and bases. You do need to know all of these characteristics, so make sure that you've listed them all out and that you can do that kind of from memory. Here's what I've got for my characteristics of acids and bases. I've also got my memory devices for the strong acids and strong bases for you. All right, there is some vocabulary to know, so make sure you know all of these vocabulary words. I'm just going to kind of click through them really quick so that way you can refresh your memory on what each of those are and compare to what you wrote down. So kinetics is the first one. Again, that's based on kinetic energy. Amphoteric, when a chemical can be both an acid and a base. And remember, acids either give away hydrogen ions, whereas bases either give out hydroxide ions or accept hydrogen ions. The rate of a reaction, again, is the speed of that reaction. A catalyst has no effect on the speed of that reaction. It's a chemical that can be added to the reactants to put them in the correct orientation, like the matchmaker in the video that I showed you. Those equilibrium values, those KEQ values, don't forget how to calculate them. So a lot of information up here. Feel free to pause the video. Organic chemistry, again, that is just the chemistry of carbon-containing molecules. Carbon is typically bonded with hydrogen, which is why these are called hydrocarbons. You do need to know how to name them, so make sure that you have reviewed that as well. Let me flip back one slide so that way you can see that. All right, and so I've got some practice for you on those. Not sure why it's here twice. All right, so taking a look, here are some organic molecules. And here are their formulas below. We can see C1, CH4, C2, H6, C3, H8. And so what would their names be? Well, so as I'm taking a look at them, the first thing I'm going to take a look at is, okay, are there, what's the longest carbon chain? Are there double bonds, single bonds, or triple bonds? And so I can see this first one, our longest carbon chain is just one carbon. So the prefix for that is meth. I see only single bonds, so the ending is ane. So this would be methane. In the second one, I see two carbons, so that's eth. Again, single bonds, ane. In the third one, I see three carbons, so that's propane. All right, so what would you name this one? Great time to pause the video. Hopefully you said 2-methylbutene. Yes, butene because of that double bond. And on this 2 carbon, we have that methyl group hanging off of it. How about this one? Could you draw a 3-methylhexane? Great time to pause the video and see what you can do. Hopefully you've got something like this. Now, could you have drawn it? I numbered my carbons from the left side, of course. So here's carbon 1, 2, 3. If you had numbered your carbons from the other side, yes, this 3-methylhexane could have been over here, and that's okay. All right, how about this one? So I see pent. So I know I've got 5 carbons, ane, so I know we've got all single bonds. I see we've got 2 side chains that are methyls, so can't come up with something like this. Again, it depends where you number your carbons from. I numbered again from the left side. If you numbered them from the right side, your molecule would look a little different. All right. Biochemistry, these are the important biological macromolecules. They're called macromolecules because they're large. You do need to know them, and you need to be able to have examples of each one. Here's the examples that I've got for you. Again, feel free to pause the video anytime you need to. So there is our carbohydrates. If we have a complex carbohydrate like a polysaccharide, it's just a chain of monosaccharides. Proteins, of course, are made of amino acids, include And if we have a long chain of amino acids, that is a protein. Otherwise, it's a polypeptide. Lipids, of course, have a glycerol molecule with a fatty acid chains. And so we'd be taking a look at those. Nucleic acids are DNA and RNA, and their monomer is a nucleotide. All right, a little solution stoichiometry. If you haven't already solved this problem, make sure that you do that. So as I'm attacking this problem, you know what I'm going to be taking a look at is I'm going to be taking a look at what information I have, and I can see that I have one piece of information about phosphoric acid and two pieces of information about NaOH. And so the first thing, of course, is to write that balanced equation. And so here is our equation. Obviously, it's not balanced. So in order to balance it, I've got to add those coefficients. So go ahead and take a couple of moments if you haven't already solved this one and see what you can do. And so as I'm solving any solution problem, I am always taking a look at my molarity triangle. I know that my molarity is my number of moles divided by liters. So that means that my number of moles divided by my molarity, which is 0.2 here. And I think I have an error here. So 0.067 divided by, because that's my moles of phosphoric acid, divided by 0.2 is going to be, hold on one second, my phone is not wanting to cooperate and give me my calculator this morning. Let's see if it will come up here. This is where I believe I have a typo in here. So that's where I was trying to get that up for you. Well, and it's just not going to come up, pop up. I did not bring a scientific calculator with me, as you're going to see a little bit later. Here we go. And I corrected this, and my computer is acting very funny this morning. So I don't believe it corrected it for you. So we are looking at needing 0.0335 liters of phosphoric acid to make this reaction work. Because again, if you take your number of moles, divide by molarity, there you go. All right, how about the equilibrium expression? How are you on equilibrium expressions, and how did you do? Hopefully you came up with this as your equilibrium expression. Good. And then how about those shifts? So for the first one, if more H2 is added, that's going to make more product, so shift it that way. If heat is increased, it would shift it the other way because we're looking at heat as a product here. If a catalyst is added, it's going to have no effect. And if pressure is increased, well, I've got to count up my moles of gas. I see 2 moles of gas here. I see, and in my reactants, I see 2 moles of gas there. So that would have no effect either. All right, how about this one? Here's another reaction. I picked this one because of, again, water is amphoteric. All right, so how would equilibrium shift if more water was added? Yes, it would shift towards the products. If the volume was increased, now I'm thinking about Boyle's law, I know that that means the pressure is going to decrease, and so it's going to go towards more moles of the gas. Well, so it would shift, there's no moles of gas on my left side. So it would shift towards that right side. All right. Oh, and then I did ask you to write that equilibrium expression there. So that way you've got that. Products divided by reactants. Of course, we're not including water in that because it is not a gas in this equation. All right, here's another one. How did you do with this one? And I do believe this was on my little list that I sent you. Hopefully you came up with that for your equilibrium expression. I'm just double checking to make sure I've got everything correct. And if you knew the concentrations of each of those chemicals, you could plug them in and hopefully you came up with an equilibrium expression of 0.3. And so that tells me that my reactants are favored here. So this equation is going to favor reactants as opposed to products. All right, then energy and reactions, drawing a chemical, the profile for an exothermic reaction. Here it is. Again, if a catalyst is added to that exothermic reaction, it's going to provide a new pathway like that one right there. Hopefully for endothermic, you drew this one. And then, of course, label all the parts, especially the axes, energy and time. Time can also be on your x-axis, reactants, products, your activated complex. All right, a little bit more organic chemistry. See if you can draw these molecules. So octane, again, I'm going to go ahead and do a carbon chain, all single bonds because of that ANE ending, 4, 5, 6, 7, 8. All right. And so I'm not really sure about this one. So if this is my 8th carbon, because it's way down here, this would be carbon 6, this would be carbon 7, and so we're going to have a methyl group off carbon 6 and carbon 7. The second one was chloropentane, so again, I'm looking at my longest carbon chain is going to be 5 carbons long. And I can see that I have a chloro group hanging off of my 3rd carbon. So there you go, 3-chloropentane. And then, of course, if you're given something like this, you would have to write out the whole reaction. So obviously these are my bases. I'm looking for my conjugate acid. Don't forget that an acid is able to give away a hydrogen ion. So I would just take each of these molecules and add an extra hydrogen ion to them. There you go. And so our water becomes our hydronium ion. All right. Now